Hi everyone, my name is Marcus Chua, and today I'm going to be talking about hydrothermal nanowire synthesis. So, by definition, hydrothermal synthesis is a technique that involves the growth of materials from aqueous solutions at an elevated temperature and pressure. So, in this context, aqueous solutions are solutions that are generally in the liquid state um, and are going to be used to grow these materials. And so the term hydrothermal usually refers to any heterogeneous reaction, so having multiple different components in the presence of these said aqueous solvents under high temperature and pressure conditions. And this allows for the dissolving and reforming or recrystallizing of materials that are relatively insoluble under normal room temperature conditions. So the hydrothermal technique is widely used for the synthesis or creation of a variety of inorganic compounds, including nanomaterials. So there are two main types of hydrothermal synthesis, each with their own steps and each with their own pros and cons. In the first method, there are only three steps, as you can see in this picture below. The first step that occurs is the deposition of zinc oxide gas to zinc oxide as a solid form. And so deposition is a chemical process that allows a substance in a gaseous state to bypass the liquid state and just immediately turn into a solid. So as you can see, this image right here is the deposition of the zinc oxide. Next, a zinc oxide seed layer is formed onto this solid zinc oxide substrate, and so this seed layer is used to produce the nanowires in a later step, and serves as the basis from which the nanowires are grown. So as you can see, these blue dots right here, that is the seed layer that I'm talking about. So finally, the third step is going to be hydrothermal synthesis. And so hydrothermal growth allows the nanowires to grow perpendicular to the substrate and grows through the seed layer. And so unfortunately, one downside to this type of hydrothermal synthesis is that you cannot control the width of the wires. And so some of these nanowires can get too thick or too thin, and it's very difficult to regulate. And so that brings us to method 2. And method 2 is pretty similar to method 1, except in method 2, we use a electron beam lithography to help us regulate that thickness of the nanowires. So similar to the first method, the processes of the deposition of zinc oxide onto the substrate and the is still going to be the first step of the procedure. So as you can see here, this is the deposition of zinc oxide. That's the first step. Second, again, we have the seed layer growing onto this deposition and growing onto the substrate. So that's the second step. Third step is where the differences begin. And so using an electron beam lithography electron beam lithography is a method of lithography using electrons to shoot off of surfaces. Using a resist, a growth mask is formed over this initial seed layer. So in this image, the yellow bit is the growth mask, which forms over that blue seed layer. The fourth step we have here is going to be an electron beam patterning within the growth mask. And so what happens in this step is that holes are created within the growth mask, as you can see here. And these holes expose the underlying seed layer, and they serve as a template for the nanowires to form out of in later steps. So at this point, hydrothermal growth begins. And so as you can see, the hydrothermal growth allows the nanowires to grow straight out of those patterns and that growth mask. And so all of these nanowires are going to be very nice and orderly and have very constant widths. And so finally, the last step is where the resist is removed, which leaves only the nanowires remaining. So now you see you have the zinc oxide nanowires with no more resist, and then you have the seed layer and substrate. So when I first thought of hydrothermal growth, the thing that came to mind was the Play Doh spaghetti maker. And so the way this spaghetti maker works is by having a large amount of the Play Doh inside the machine, and then the Play Doh passes through a filter, which is probably this blue or orange thing right here. And when it comes out the other side, it's separated into smaller ropes of Play Doh. And this is because the filter contains many, many small holes that serve as a guide from which these spaghetti noodles can be formed from. And so after this process, the spaghetti noodles can then be removed from the filter and just be kind of on their own. And so the growth mask in hydrothermal synthesis is, I'd say, kind of like the filter, and the spaghetti is kind of like the nanowires, and the initial Play Doh inside the machine is like the overall zinc oxide substance. So with that second step of hydrothermal synthesis, you kind of first have the growth mask being, you can have the growth mask being removed, which is similar to the spaghetti maker, and the nanowires can also be isolated, just like the filter can be removed and the Play Doh noodles can be kind of separated and isolated on their own. So the filter is kind of like kind of acts like the growth mask in this situation, because like the growth mask, it can allow it can serve as a template for the material to pass through and form these nice orderly noodles, or nice orderly wires. Alright, so hydrothermal synthesis is a fairly specific practice, and it's specifically used to grow nanowires and other nanostructures. And so as a technique, it is beneficial because it allows for processing at relatively lower temperatures than other similar techniques to synthesize nanowires. And it allows for growth on many different substrates. So for example, here you have, we have silver, you have titanium, you have copper, and you have different types of substrates that the nanowires can grow on. So because of these benefits, hydrothermal synthesis is widely used by geologists, biologists, physicists, chemists, ceramists, material scientists, engineers, and other professionals and scientists. So that is all I have to say about hydrothermal nanowire synthesis. Thank you for listening to my presentation.